One very specific example of differential equations and exponential growth and decay has to do with cooling objects and Newton's law of cooling. At the end of this lesson, you'll be able to use Newton's law of cooling to solve problems involving cooling objects. Alrighty, Newton's law of cooling states the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Alright, so we're going to try to take this information, write a differential equation, and then let's see if we can solve it. Okay, it says the rate of change in the temperature of an object. So rate of change we know is a derivative and it's changing with respect to time, so we're going to put d, and I'm going to put d T sub O, that has to do with the temperature of the object, over d little t, and the little t has to do with time. And then since it's proportional, we know there's some sort of proportionality constant, and it's proportional to the difference between the object's temperature and the temperature of the surrounding medium. So it's going to be, the constant's going to be multiplied by the difference between the object's temperature, so T sub O, minus the temperature of the surrounding medium. So temperature and surrounding medium means like the room. Is it in a room? Is it in a refrigerator? Is it in a hot coffee pot? Where is it in? So that's what we're talking about with the temperature of the medium. Okay, now we are going to attempt to solve this problem, and we are going to solve it for T sub O. That's our goal. All right, so I'm going to go ahead and cross multiply. And just to point out too, K is a constant in this problem, and actually the temperature of the medium is also a constant because we're going to assume that that's kept at a constant temperature, whatever it is. Okay, so I'm going to get dt sub O is equal to K T sub O minus T sub M dt. All right, I noticed that we need this T sub O over with this one, so I'm going to divide it from both sides. All right, so now I'm going to have d T sub O over T sub O minus T sub M is equal to K dt. And now I do have my variables on the right side, so we're ready to go ahead and take the integral of that. On the left side, since I have more than one thing in the denominator, I do need to do a u substitution. So I'm going to let u equal T sub O minus T sub M. When I do that, the derivative of it, the derivative of T sub O is just 1. The derivative of T sub M, since that's a constant, would just be 0. So and this would just be dt sub O. And so now I have exactly what I need. So this really is a du over u problem, and the integral of du over u is the natural log of my u, which in this case happens to be T sub O minus T sub M. And then we'll equal, on the right side, the integral of k will be kt plus c, just like we were used to in those other problems. All right, we would like to solve for T sub O, so I'm going to do the logarithm loop again. So I'll get e to the kt plus c is equal to T sub O minus T sub M. I'm going to bump my c out front, so I'll have c e to the kt is equal to T sub O minus T sub M. And if I'd like to solve this for T sub O, I will just add T sub M to both sides. So we'll get T, temperature of the object, is equal to C e to the kt plus the temperature of the surrounding medium. Right? This is the formula. Now that we have done the calculus behind Newton's law of cooling, when we do the Newton's law of cooling problem, we do not need to do all of this solving a differential equation every time. Just like we did on the exponential growth and decay problems, we can actually just use this formula. Alrighty, so let's go ahead and dig into some problems. All right, we're going to start with a hard-boiled egg. It's at 98 degrees Celsius. It's put into a sink of 18 degrees Celsius water. After 5 minutes, the egg's temperature is 38 degrees. Assuming that the water has not warmed appreciably, how long will it take the egg to reach 20 degrees Celsius? I'm guessing that maybe some sort of chef might want to know this information, so that's why for the chef we'll go ahead and do this problem. All right, since we know that the egg is cooling, we will go ahead and write down that formula that we will just appreciate the calculus behind. Okay, and one thing that I can go ahead and do right now, I know the temperature of the surrounding medium, and that is, it is put into a sink of 18 degrees Celsius water. So that's the temperature of the surrounding area. So we're going to put temperature of the object is equal to C e to the kt plus 18. Okay, now from here, just like we did in all the other problems on the exponential growth and decay, we will find C, and then we'll find K, and then we will solve the problem. Okay, so the first thing we need to do is find C. We know that when we started out, this hard-boiled egg was 98 degrees Celsius. So the temperature of the object was 98 degrees, and that was at time equals 0. Okay, to solve for K this time, I will need to subtract 18. So I'm going to get 80 equals C, and then e to the 0 is just 1. So C is equal to 80. All right, so now we're ready to rewrite our formula again. We're going to get T sub O equals 80 e to the kt plus 18. Now I need to find K. It did tell us that after 5 minutes, the egg's temperature has drastically reduced to 38. So from here, we can go ahead. The temperature of the object is now 38. It took 5 minutes for that to happen. Okay, and now we will be solving for K. So I'll start by subtracting 18. Then I'll get 20 equals 80 e to the 5k. From here, I'll divide both sides by 80. So I will get 20 divided by 80 is 0.25, and as long as that's an exact decimal, I can use decimals. And we'll get e to the 5k. Just like we have done in all the other problems, we'll take the natural log of both sides. So I will get the natural log of 0.25 is equal to 5k ln e, and we know the natural log of e is 1. If I divide both sides by 5, I now know that k is equal to ln of 0.25 over 5. All right, so my new formula is now y equals 80 e to the ln 0.25 over 5 t plus 18. So I found C, I found K, and now let's see if we can answer the question. How long will it take the egg to reach 20? So I want to know, when will that temperature, whoops, this should have been T sub O. When will that temperature equal 20? So solving this for T, first thing I'll do is subtract 18. So I'll get 2 is equal to 80 e to the ln 0.5 over 5, 0.25 over 5t. The next thing that I want to do from that, I'll divide both sides by 80. So I will now get 1/40th, and I'm just going to leave it as 1/40th, e to the ln 0.25 over 5 times t. From here, just like we've done in all the other problems, we'll take the natural log of both sides. So I'll now have the natural log of 1/40th is equal to t, well, actually, let's do that whole exponent, ln 0.25 over 5 times t, ln e. The natural log of e is 1. And then to solve for t, we can just multiply both sides by the reciprocal. So we'll multiply 5 over ln 0.25, and the same thing over on this side, 5 over ln 0.25. And when I plug that into my calculator, I should get 13.305 minutes. So that's how long it would take that egg to cool to 20 degrees. Alrighty, let's try another one. Let's do a little CSI here. A detective is called to the scene of a crime where a dead body has just been found. She arrives on the scene at 10:23 p.m. and begins her investigation. Immediately, the temperature of the body is taken and is found to be 80 degrees Fahrenheit. The detective checks the programmable thermostat and finds that the room has been kept at a constant 68 degrees for the past 3 days. After evidence from the crime scene is collected, the temperature of the body is taken once more and found to be 78.5 degrees Fahrenheit. This last temperature reading was taken exactly 1 hour after the first one. The next day, the detective is asked by another investigator, what time did our victim die? So what's the time of death? Assuming that the victim's body temperature was normal at 98.6 degrees Fahrenheit prior to death, what is her answer to this question? So the body is cooling, so we can go ahead and use Newton's law of cooling. So we're going to have the temperature of the object is equal to C e to the kt plus the temperature of the surrounding medium. And in our case, the surrounding medium would be the room that the body was found in, and the room was kept at a constant 68. So we can just put a plus 68 there. Alrighty, just like we've done in all the other problems, we'll find C, we'll find C, we'll find K, and then we'll solve the problem. All right, so finding C, we know that when the temperature of the body when it was found, the temperature was 80 degrees. So we're going to put 80 equals C e to the K, was that time equals 0. and that would just be 0. If I subtract 68 from both sides, I have just found that C is equal to 12. Excuse me. And then from here, we now have the temperature of the object is equal to 12 e to the kt plus 68. Okay, next thing I need to do is find K. I do know that the body temperature was taken again and found to be 78.5, and that was 1 hour after the first temperature reading. So we know that the temperature is now 78.5, 12 e to the k times 1 plus 68. So now we're going to solve for K. So subtract 68 from both sides, and when I do that, I will get 10.5 is equal to 12 e to the k. From here, I'll divide both sides by 12, and since that doesn't work out to be a really nice decimal, actually it does. 10.5 divided by 12 is an even 0.875, so we actually can use that as a decimal since I didn't have to round it all, and that's going to equal e to the k. And then to get rid of the e, we'll take the natural log of both sides. So we'll get the natural log of 0.875 is equal to k ln e. The natural log of e is 1. So we know that k is equal to the natural log of 0.875. All right, so now we know that the temperature of the object is equal to 12 e to the ln 0.875 times t plus 68. And now from here, we're going to attempt to answer the problem. It says, what is the time of death? When did the victim die? And we know when the victim died, the temperature of the body was a 98.6 degrees. So now we're going to put 98.6 is equal to 12 e to the ln 0.875 times t plus 68. And we're going to be trying to solve for t. So I'll start by subtracting 68 from both sides. So I will get 30.6 is equal to 12 e to the ln 0.875 times t, and then I'll divide both sides by 12, and that also works out to be a very nice answer. That's just 2.55, and again, since it's an exact decimal, I can keep it as a decimal. Otherwise, I just leave it as that messy fraction. So 2.55, and that will equal e to the ln 0.875 times t. The next thing that I want to do is take the natural log of both sides. So get the natural log of 2.55 is equal to ln 0.875 times t ln e. The natural log of e is 1. And then to get t by itself, we'll just divide both sides by the natural log of 0.875. And when I do that, I will get t is equal to negative 7.01. And the reason that I got negative is because obviously the victim died before they came in and found the victim. So this was 7 hours, a little over 7 hours prior to when they found the body. So if we would like to figure this out, 7.01, this does not mean, the 0.01 does not mean 1 minute. What we need to do to figure this out, it's going to be 7 hours. And then we take 0.01 times 60, since there are 60 minutes in an hour, and when you do that, you will get 1 minute. So it did work out nicely that was this, but it doesn't always work out that way. So 7 hours and 1 minute prior. So if they found the body at 10:23, and we subtract 7 hours and 1 minute, we will be at 3:22 p.m. was the estimated time of death. So hopefully now you can solve a Newton's Law of Cooling problem.